you know that the sky is a mysterious ocean? One that humanity may never fully explore? Since ancient times, humans have likened the stars to gods, beings with superhuman powers capable of ruling mankind. But those were just myths, not reality. Since the rise of science, pulling humans out of the Dark Ages, we have always tried to separate mythology from truth and focus on explaining the universe using the laws we discover. Yet, as science developed, suddenly the ancient stories about gods became strangely tangible. Could it be that all of it leads to the idea that somewhere out there truly is a supreme being who designed everything? Speaking of geniuses, certainly AI among us also immediately thinks of names like Einstein, or even Tesla. Even geniuses are human, and humans have their flaws. In his years of research and exploration of the universe, Einstein made groundbreaking predictions that helped humanity advance in exploring the world. However, alongside these achievements were mistakes that Einstein himself admitted were the stupidest moves he ever made. To talk about that stupid move, we need to go back to the time when Einstein was not yet the most illustrious scientist. This was the time when Einstein's theory of relativity was newly published, and the scientific community did what scientists do best. They refused to accept it. The essence of science is experimentation, testing to verify, rather than trying to assert that something is true. Science tries every way possible to prove it wrong, and once it cannot be proven wrong, it is certainly correct. This absurdly meticulous scrutiny is the fine line that distinguishes science from pseudoscience, because true science must follow rules, fixed laws, and never rely on random coincidences for explanations. So when Einstein proposed relativity, which had the potential to overturn all scientific work since Newton, the scientific world rigorously and meticulously tested it in every possible way. And through calculations and experiments, Einstein's relativity gradually emerged victorious when facing Newton's laws. One of Einstein's greatest triumphs was when scientists applied Newton's law of motion to Mercury. According to Newton's laws, an object moving in a vacuum, unaffected by external forces, should not change its speed or direction. Mercury moves in a vacuum around the sun, meaning its orbit should remain unchanged. But strangely, Mercury's orbit changes over time. Meanwhile, Einstein's theory of relativity claimed that space and time are one, a stage 4 particles to perform on. Essentially, the sun is a massive particle that warps space-time, causing other particles, specifically planets, to fall into its gravitational well. Like objects caught in a whirlpool, planets cannot maintain fixed orbits, allowing us to explain Mercury as a unique orbit, and indeed the orbit of any celestial body. Something Newton's laws alone struggled to fully explain. In short, Newton's laws can describe the motion of matter in the universe with reasonable accuracy. But Einstein's theory explains the core of motion, allowing us to predict how matter moves in a vacuum. Einstein's relativity does not replace Newton. Rather, it perfects his work. From there, scientists gradually accepted relativity as the foundation of astronomy and space science, applicable to a wide range of research fields. But this is where problems began. If Einstein's relativity perfectly models the universe, that matter affects time without curving it or creating gravity, wouldn't the universe collapse? Simply put, if gravity were the only force, the universe would have contracted over 13 billion years, and instead of galaxies, stars, and magnificent nebulae, it would be a massive black hole, silent and lifeless. Yet we are alive, stars still shine, and nebulae fill the sky. So Einstein's relativity wrong. To address this, he proposed the concept of the cosmological constant, denoted by lambda, a force counteracting gravity. This constant prevented gravity from collapsing the universe, effectively holding everything in a static state. It may sound abstract, but in reality, the existence of this constant seemed as though Einstein invented it to cover his mistake. That there is a force counteracting gravity sparked new debates about the laws of the universe, suggesting that relativity, like Newton's laws, might still be incomplete, or perhaps, in all these calculations and predictions, we overlook the most important fact. We are only human, and the universe is too vast to be reduced to small laws. Einstein might have been right that some force prevents everything from collapsing, but he might also have been wrong, that the world is larger than his equations. Whatever the case, science remains science. and its greatest task is to experiment, question, and find answers. So the question arises, if the universe is not static as Einstein proposed, what is it like? Relativity assumed the universe was static, with matter orbiting endlessly, unaffected by the vacuum. To ensure gravity did not destroy this perfect picture, Einstein introduced a cosmological constant to balance gravity. However, this was neither the first nor the last time anyone assumed a static universe and analyzed it thoroughly. Before Einstein published Relativity, many scientists had looked at the sky, questioning the stillness of space. A simple question: why must stars be static? Why did we not doubt this assumption? Perhaps we all deluded ourselves into thinking the universe must be perfect, created by God, with everything in an ideal state to satisfy our intellect. But reality always lies beyond imagination. Since the genius of William Herschel, a German composer and astronomer, discovered infrared radiation in 1800, the world was never the same. Other great minds expanded upon the concept of infrared to explore the full spectrum of light, from visible to invisible. Light, like other waves, has a frequency which determines its color. The visible spectrum ranges from red to blue, weak to strong. Higher frequency means blue, lower frequency red. Stronger than visible light is ultraviolet UV, then X-rays, and then gamma rays, used to destroy cancer cells. Conversely, weak light becomes infrared, microwaves, and finally, radio waves. Astronomers use light movement to measure distance and speed of objects. A blue, rapidly flashing light means the object is approaching at an incredible speed. Red and dim means it is receding. In 1912, American astronomer Vesto Slipher found a bright point of light in the sky. Blue, meaning it was coming toward us, flashing at a terrifying speed of 300 kilometers per second. Such speed and light intensity indicated it could not belong to our galaxy. It was an entire galaxy itself, Andromeda. Subsequent studies revealed many other galaxies moving at astonishing speeds. By 1922, Slipher discovered another galaxy receding at 2,000 kilometers per second. Too many galaxies moved differently, unevenly. If the universe were static, there would need to be orbits, right? Slipher was not the first, nor the only one to look at the sky and inadvertently discover evidence of an expanding universe. In 1922, Russian astronomer Alexander Friedman developed equations based on Einstein's work, proposing that the universe could expand, and even calculating the rate of expansion. Then, Edwin Hubble, an American astronomer, clarified the story, measuring distances to newly discovered galaxies and comparing their redshifts. He revealed the terrifying reality. Distant galaxies were receding faster than nearby ones. This did not mean Earth was the center, but that space itself was expanding. Everything was moving apart, and the farther an object, the faster it recedes. Hubble's discovery stunned scientists, challenging the static model and shaking Einstein's theory. After independent verification, Hubble's work was accepted. The universe is expanding at an incredible rate, though exactly how fast remains uncertain. Scientists have continued trying to determine the rate, initially estimated at 500 kilometers per second per megaparsec. But it varies, and the quest for the Hubble constant continues. The fact remains: the universe is expanding, and Hubble's work proved it. He continued research at the observatory until his death in 1953, leaving a monumental legacy with the Andromeda Galaxy and the constant. Hubble helped determine the universe's age about 19 billion years. The Hubble Space Telescope was launched, showing supermassive black holes, but also wondrous phenomena, dark matter. This is only half the story. Cosmic light that if the universe expands, to what extent? Expansion proves a beginning. Everything was once incredibly small, denser than a black hole's core, hotter than anything we've seen. That beginning was a singularity, a point containing all. Yet doing nothing, space and time did not exist yet. Then came light. The Big Bang released all matter, creating time and space. In the first moments, matter spread. The universe's density decreased. Particles had space to move, and temperature dropped, allowing formation of light elements like hydrogen and helium. Heavy elements formed later, influencing space-time to create gravity and pull lighter elements together, forming rocks, stars, and planets, the universe continued expanding, leading to the cosmic expansion we observe today. This Big Bang theory explains nearly all astronomical phenomena, though many questions remain, like the exact expansion rate. It also opened the way for future scientists. Some argue it implies God's existence, while others propose cyclical models, big bounce, where the universe collapses and re-expands, avoiding the need for divine creation. In the 20th century, humanity reached the height of science. Einstein proposed relativity. Quantum mechanics emerged. We can calculate and predict the motion of stars and planets using relativity, and the behavior of particles using quantum mechanics. But these two robust theories are incompatible. They operate independently. Relativity cannot explain quantum interactions, and quantum mechanics cannot explain cosmic scale phenomena. Thus, both remain incomplete. The next mission for humanity's greatest minds is the unified theory. To unify relativity and quantum mechanics into one theory explaining all phenomena from the smallest to the largest. Quantum mechanics and relativity are fundamentally different, and creating a unified theory remains a monumental challenge.
Come at me and you won't get any older, dude. Crack your holder too. Heating up inside of me, blood so violently. Thanks for trying me. Now it's finally time to see how this rivalry becomes a